Okay, so x of 0 equals 1. Now, I'm exaggerating the distance here compared to the distance here because I didn't want to use the whole board to make the amplitude small compared to the length. And we know that the amplitude for this model to work has to be small compared to the length. Otherwise, you don't have a constant restoring force. And of course, we only have an approximately constant restoring force. You could also think of a mass on a spring, but the spring's got mass. That could mess things up, depending whether it's vertical or horizontal. If it's horizontal, you got friction, so you're dealing with an ideal case in just about anything you do, right? Okay. Okay, so x of 0 equals 1. That's going to look like this. Okay, well, now, what's going to happen next?
I guess it's going to, as t increases, it's going to move further and back, so it's got to get...
Well, what's happening to the number that you get when you evaluate the position, which of course is on this axis, right?
Right.
What's happening to that number?
It's decreasing.
It's decreasing, so what's that going to do in your graph?
It's going to cause it to go back.
Yeah. Okay? Once you get yourself oriented to what this thing is, how this relates to this,
Right.
okay, it becomes fairly straightforward. The other thing is the thing stationary here?
Yeah.
I don't think so.
No.
He's
No.
wrong. What do you think?
No.
I would have to say no then.
It was already moving.
Why is it already? How do you know it's already moving?
It's got a higher position before time starts, I guess.
Because it's not at position 0, right?
How about the fact that this graph has a non-zero slope at t equals 0?
That'll work.
You have a positive or negative velocity.
Positive. Oh, wait.
No, it should be a
Negative.
negative velocity.
You're kind of on a
'cause
roll there.
it's
Yeah,
going
you know.
down.
Okay.
Uh,
Okay, so this thing is also moving, right?
get up there.
If this is the picture.
You laughing, man.
It's
I've
okay.
already messed up today.
You
so
see
it's
me.
okay.
You see me in much more shape than that, and just about every day, at least once a week, and usually several times. Okay, so you have this, right?
Yeah.
Okay, well, what's going to then happen? Now, if you have
It's
a
gonna-
pendulum in air, or where drag is negligible, what's going to happen?
It should come back to that position at some point, right?
Well, yeah, but what's it going to do before it comes back to that position?
Well, it's got to go to the other starting
Yeah, it's going to go
point.
right through 0 to the other side. How far is it going to go on the other side?
Negative
And
1.
equal distance, negative.
No, it's not equal distance because it's got velocity here.
Oh,
Farther than negative 1?
Huh?
Farther than negative 1?
Yeah. It's got to go past this point, right?
right,
Think of the kinetic and potential energy as we analyzed it in physics, right?
right.
And try to improve your intuition about simple harmonic motion. Okay? You have a potential energy because you're here, and you have a kinetic energy, and the total energy is therefore greater than the potential energy at this point.
Right.
If gamma is 0, it's not going to lose any energy. So it's got to move to a point over here where its potential energy is the total of the potential and kinetic energies at this point, right? Now that's a digression into physics, but you really need to understand that. And also for physics, because we're moving into circuits. And they're direct analogies with this simple harmonic motion. You're going to see in circuit AC circuits. They're all driven by simple harmonic motion, right? Really important. So, we need these tools. We need to be able to interpret this. So we want to work on that. Okay, so anyhow, yeah, if there's no drag. Now, what happens here?
Well, your x1 is approaching 0, right?
Yeah, it's going to go to 0, but it's going to approach 0 asymptotically. It's never going to get there. Okay? That makes sense? Maybe. Okay? So, then, so we approach x equals 0. Asymptotically, and that's our interpretation of that particular function.